Section: Introduction. In this section, we discuss the increasing use of deep learning models in healthcare, where errors can have serious implications. To enhance the safety and reliability of these models, we emphasize the importance of interpretability, which allows us to explain model decisions in a way that is understandable to humans. Various interpretability methods exist, and we focus on concept-based approaches that use familiar high-level terms for explanations. We introduce TextCAVs, a method that relies solely on text labels or descriptions of concepts instead of image examples, which can be costly to obtain in medical fields. We demonstrate that TextCAVs provide valuable explanations for tasks involving natural images and chest X-rays. Additionally, we show how interpretability can help us identify biases in deep learning models, particularly in the Mimic-CXR dataset. In related work, we note that previous methods like TextCAVs use probe datasets to create concept activation vectors, CAVs, and measure model sensitivity. Our approach differs as we create CAVs using a multimodal model without needing a separate probe dataset for each concept. While other methods automate concept discovery, they often require visual presence in the dataset, which our method avoids by deriving meaning from text descriptions. We leverage clip models, which excel in vision language tasks, allowing us to compare text and image features effectively. Our method does not impose restrictions on the architecture or training of the target model. We also reference other works that utilize multimodal models to create CAVs, but our focus remains on explaining the model's current state rather than altering its inference process. To create TextCAVs, we train linear layers to convert features between our target model and a clip-like model. We use a cycle loss to ensure consistency when converting features back to their original forms. Once trained, we can generate concept vectors using just the text label of the concept. By calculating the directional derivative, we assess the model's sensitivity to specific concepts without needing image examples, thanks to the linear relationship between the penultimate layer and the output. By ranking concepts based on their sensitivity, we can identify potential issues in the model. This process allows for quick testing of new concepts, enabling an interactive approach to model debugging, ideally guided by human experts who can apply their domain knowledge. Section Summary. In this section, we introduce TextCAVs, a concept-based interpretability method that generates explanations using only text labels instead of image examples, making it more cost-effective for medical applications. We demonstrate its effectiveness in providing meaningful insights for both natural images and chest X-ray tasks, while also aiding in debugging deep learning models by identifying dataset biases. Section: Experiments. In this section, we describe our training setup, model choices, evaluation, and analyze our results from experiments with both the ImageNet and Mimic-CXR datasets. For ImageNet, we achieved third place in the interpretability competition at the Secure and Trustworthy Machine Learning Conference, where we demonstrated that our method, TextCAVs, could detect hidden issues in vision models trained on ImageNet. We also successfully identified all 4 secret Trojans, showcasing its potential for interactive debugging. Here, we focus on showing that TextCAVs can provide reasonable explanations for a standard RESNET50 model trained on ImageNet. In our training details, we utilize 20% of the ImageNet training dataset to train our models for 20 epochs. We used the default weights for our RESNET50 from the Torch Vision package in PyTorch as our target model. For the vision language model, we employed a pre-trained VIT-B16 clip model. To automate the concept extraction process, we followed a method similar to Oikarinen et al. We used a large language model, LLM, to generate a list of concepts by prompting it for common visual elements and superclasses in ImageNet. We filtered the concepts by removing plurals, articles, and those with more than 2 words. We further refined the list by eliminating similar concepts based on their text embeddings, keeping only the shortest concept when their similarity was high. We used a quantized version of the Tulu v2-7b model for this task. In our results, we present the top 10 concepts for selected ImageNet classes, all of which are relevant to their respective classes, indicating that TextCAVs can generate reliable explanations. For the Mimic CXR dataset, we demonstrate TextCAVs' ability to provide meaningful explanations for a model trained on chest X-rays and how it can help identify bias in a model trained on a biased dataset. In our training details for Mimic CXR, we trained both linear transformations and the target model using the Mimic CXR training set. The target model was a RESNET50 pre-trained on ImageNet and fine-tuned for multi-label classification of chest X-rays, including classes like no finding and atelectasis. We used the ADAM optimizer with specific settings for weight decay and learning rate, adjusting the learning rate based on validation loss. We augmented the images through various techniques and used published data splits, resulting in a training set of 368,945 images. For concept extraction, we utilized clinical reports associated with each image, specifically extracting sentences from the findings and impression sections. We randomly selected 5,000 sentences to gather a diverse range of concepts. To assess TextCAVs as a tool for interpretability, we introduced a dataset bias in the Mimic CXR training set by excluding participants with a positive label for atelectasis who did not have a support device. This means that all participants with atelectasis in the training set also had a support device, as illustrated in our figures. Section Summary. In this section, we describe our training setup and model choices for evaluating TextCAVs on the ImageNet and Mimic CXR datasets, highlighting its success in detecting Trojans and producing reliable explanations for a RESNET50 model. We also demonstrate TextCAVs' ability to identify biases in a model trained on a biased version of the Mimic CXR dataset, utilizing clinical reports to extract relevant concepts. Section: Metrics. In this section, we provide a quantitative metric by labeling the top 50 sentences for each class based on their relevance to the class, using a measure called the Concept Relevance Score, CRS. This score represents the proportion of sentences that relate to the class. For instance, with edema, we labeled a sentence as related if it directly diagnosed the condition, like worsening cardiogenic pulmonary edema, or if it implied the condition, such as bilateral parenchymal opacities, or there is alveolar opacity throughout much of the right lung. We compare two models, one trained on the standard Mimic CXR dataset and the other on a biased version, which we refer to as standard and biased. The standard model achieved a mean area under the receiver operator characteristic curve, AUC, of 0.83, while the biased model had a mean AUC of 0.81. We expect the biased model to perform better on a biased test set, particularly for support devices, which are easier to detect. Our reference model achieved an AUC of 0.92 for support devices. In our findings, we present the 5 sentences with the highest directional derivatives for the classes of no finding, atelectasis, and cardiomegaly. Some sentences clearly relate to their classes, like the lungs are clear, for number finding, while others do not, such as nasogastric tube extends below the hemidiaphragm, for atelectasis. The noise in these explanations may arise from various factors, including unexpected features used by the model, imperfect feature conversion, or inherent noise in gradient vectors. Despite this noise, our tool remains useful for detecting dataset bias in Mimic CXR. We also show the top 5 sentences for the biased model, where the bias is evident as all top sentences for atelectasis refer to support devices rather than the class itself. The CRS values further highlight this bias, with a score of 0.04 for atelectasis in the biased model indicating that very few of the top 50 concepts relate to the class. Additionally, we labeled whether the sentences referred to support devices, finding that 13 out of 50 concepts were related to support devices in the standard model compared to 44 out of 50 in the biased model. This demonstrates that TextCAVs are sensitive to the behavioral differences between the two models.